All right, this is the second installment of how to locate an earthquake epicenter. So, I wanted to revisit the terms seismic waves and talk about the classification scheme here. So, we have three different varieties of seismic waves, actually, two main types, but each type can be differentiated further. So, the two types are body waves and surface waves, and they're named for what they sound like. Body waves are energy waves that travel through the Earth's interior, whereas surface waves are energy waves that travel only on the Earth's surface. And consequently, those would be closest to an earthquake epicenter. So, when we look at seismic waves, we can use them to determine distance to an earthquake in real time. So, the P waves, short for primary, for obviously reasons. Primary waves are the first set of waves, or the first beam of energy that radiates out from an earthquake epicenter. So, because they travel faster, they will arrive to a recording station, which is the seismograph, first, right? So, depending on where the seismograph is located, if it's close to an earthquake epicenter, those waves will arrive within a matter of seconds to minutes. Far away, obviously, it's a different story because distance is related to time, as you know. The second set of energy waves, also that travel through Earth's interior, are the S waves, and the S is short for secondary, for obvious reasons. These would be energy waves from an earthquake that travel a little bit slower and have unique set of properties that I describe in a different lesson. So rather than the compressional waves like the primary, these are transverse waves, the secondary waves, and they're slower and also can't travel through liquids, which is important because there are parts of the Earth's interior that are liquid, for example, the Earth's outer core. So the S waves are second to arrive to a recording station. And then lastly, the surface waves, which travel only on the Earth's surface, are the slowest, and they will be the last to arrive at a recording station, but they have the highest amplitude because they're felt closer to the surface, obviously. And this typically will only happen close to the earthquake epicenter. So you're not going to get surface waves hundreds of miles away from the epicenter, nor are you going to get them on the opposite side of the earth. So, what does that look like? So, the seismograph is the equipment that records this energy. A seismogram is the printout that you receive that denotes the arrival of the first P waves, S waves, and closer to the epicenter, the surface waves. So if you look at this seismogram, which is the printout, you've got the arrival of the first P waves there. They're lower amplitude but faster, followed by what we call lag time. And I'm just going to denote that here in green. So this right here, it's hard to see, would be the lag time, or the time interval where that seismograph is not receiving any of the energy from the earthquake. And that lag time is separated then by another series of seismic waves, the S waves, followed by possibly those surface waves if they're closer to the earthquake epicenter, right? And so what's important here is that there is something we call lag time that exists between the arrival of the first P wave and the first S wave. And so we can measure this lag time and determine exactly how far away the earthquake epicenter was because we know how fast these waves travel. So here's the arrival of the first P wave, and then here's the arrival of the first S wave. And if each one of these bands represents 1 minute time, This would be like 1 minute, 2 minutes, 3 minutes, 4 minutes, and then 4.5 or 5 minutes total. So there's 5 minutes lag time between the arrival of the first P wave and the first S wave. And so because we know the rate of travel of these seismic waves, what we can do is we can take that lag time and we can use it to determine distance to an earthquake epicenter. So let's say, for example, that the lag time for New York, New York, which is where the seismogram is recorded, is 5 minutes. But then the lag time for Nome, Alaska, and Mexico City are different. We can use each of those 3 locations to determine exactly where that earthquake happened. So these differences in lag time correlate with distance to the epicenter. And the idea here is that we need 3 cities in order to triangulate the position of the earthquake. Okay? I don't know if this is making a whole lot of sense. It does to me, but I've learned this for 20 years or known it. So here's New York, New York. 1, 2, 3, 4, 5 minutes of lag up there. Whereas Nome, Alaska would be 1, 2, 3, 4, 5, 6, about 6.5 minutes, or 6 minutes and 30 seconds. And then Mexico City would be 1, 2, 3, 4 minutes. So just based on those seismograms alone, I know that the earthquake happened closest to Mexico City and farthest from Nome, Alaska. But then I don't know exactly where in the world this earthquake happened. So check it out. We can use a time travel graph to look at the arrival of P waves and then the arrival of the S waves. So here's your P wave curve right here, right? This tells us how fast P waves travel. And then your S wave curve tells us how fast. Oops, that's not really good. Sorry. Get rid of that. You can just look at those 2 lines. The blue line is the P wave travel time, and the purple line is the S wave travel time. And so what we're looking at there is the difference in time between those 2 velocities. So check it out. We're looking at this. So this would be an example of the travel time or lag time for New York City. Right? So New York City, New York is located, according to this graph, approximately 3,700 kilometers from the earthquake epicenter. Okay? So then what we would need to do is use a map to then triangulate the position of the earthquake. Now, I realize that you guys don't have compasses to do this at home, so you're just going to have to bear with me. But if you look at New York and you use the scale provided below, which you can actually use, just take a Post-it and line it up and measure out 3,700 kilometers, and then take that Post-it and kind of simulate a circle around your city. You're going to draw a circle that represents anywhere that that earthquake could have happened relative to New York. Okay? So the earthquake could have happened, I'm going to use yellow so it pops out. Could have happened here, it could have happened here, it could have happened here, anywhere in that circle, right? Not within, but like on the circle. That's not helpful at all, because that means the earthquake could happen pretty much infinitely within that, right? So we need a second city, Mexico City or Nome, Alaska, to determine location. So Mexico City, using the lag time, was 2,900 kilometers from the earthquake epicenter, which tells me that we now have 2 possible locations for that earthquake. The intersection between the New York City circle and the Mexico City circle, or the intersection over here between those two circles. So that's helpful because it eliminates a lot of possibilities, right? Well, if we add a third circle to the equation, that's where the magic happens, right? So when you add a third, and we look at Nome, Alaska, Nome, Alaska had the greatest lag time and is 4,400 kilometers from the earthquake epicenter. X marks the spot. There's only one place where those three circles intersect, and that one place marks the location of the earthquake. Okay. So hopefully this makes sense. Triangulation meaning you have to have at least 3 sets of data to locate an earthquake epicenter. Now, obviously, we have computers that can do this in real time today. In the past, this is how geologists would individually locate an earthquake. So in my last video today, I'm going to go ahead and show you earthquake activity for the year 2018. And you can always look up, like I said, in real time where earthquakes are happening on the usgs.gov website. So signing off for now. Peace out. Bye.